Okay, this wants us to graph an absolute value function for this. Now, you can always revert back to, all right, let me take 2 points, plot each of, or pick values for x, plug it in, figure out what the y value is. But the thing about absolute value functions, if you haven't already, you can graph these on your graphing calculators. You just have to go to math and numbers, absolute value, which I think is 1. But the important part here is all absolute value functions, their graphs create a V. That's not a V. They create a V, okay? So what's important here is in that V, that point of that V, and it could be an upside, it could be a normal V, okay? Or it could be an upside down V. So what's important with that is we have to find what that turning point, that V point is. And that's called your vertex, that turning point, where your graph goes from increasing to decreasing or vice versa, from decreasing to increasing. So to find your vertex, you're given, first off, you have to know your standard form, which is f of x, which we know is just function notation for y, equals mx plus b plus c. Okay, so using this, our vertex, which again you already have written down, is negative b over m parentheses c. So using my standard form of a absolute value function and my vertex here, I can find my vertex. So my b, okay, is this term, so I have to do opposite b, so it's going to be negative 1 over my slope, my m. M is the coefficient of your x term, which if you look here, there's none written there, so we know it's a positive 1. And then my c term is out here. So because this is plus c and this is minus 2, c is negative 2. So our vertex is negative 1, negative 2. So I'm going to plot that point. Okay, now, right now you might not know if this graph is supposed to open up or down, but I know it's supposed to be down, and that's what we'll talk about in class and as things progress here about how to translate these graphs. But because there's a negative out front of the absolute value, that means it's a negative graph. All negative graphs open down. So what I told you to do though is we need more specific points. So let's now plug in values for x. What value should you choose? Well, I always like to use at least one value to the left and one value to the right of our vertex to just see what it looks like. So here we have negative 1, negative 2, so I'm going to plug in negative 2 in for our x up here and see what y produces. So negative 2 plus 1 is negative 1. The absolute value of negative 1 is positive 1. But positive 1 times a negative is negative 1. And then negative 1 minus 2 is negative 3. So when x is negative 1, y is negative 3. So I'm going to plot that point as well. And then let's pick a point to the right of our vertex here. So I'm going to pick 0. When x is 0, okay, 0 plus 1 is 1. The absolute value of 1 is 1. 1 times a negative is negative 1, and negative 1 minus 2 is negative 3. So we get the ordered pair 0, negative 3, which works because all absolute value functions should have symmetry. So if the one to the left is down 3, then the one that's only 1 to the right of it should be down 3 as well. So then I can graph my line. And if you're not comfortable with that and want to test another point, by all means do that. But you only need those 3 points to graph an absolute value function graph. Okay, so then that's example 1 for you. And then example 4, because example 2 is just graphing an absolute value function in your graphing calculator, which you just go to y equals, type in exactly as it is, and hit graph. And then example 3 is how to graph it using other stuff that's not relevant, because the goal of this lesson is to graph absolute value functions. Why do you need to know how to do it 5 different ways? Example 4 says you can use absolute value functions to model time and distance problems. You can consider the time before you arrive at a destination to be negative. So what they're talking about here, a train traveling on a straight track at 50 miles per hour passes a certain crossing halfway through its journey each day. Sketch a graph of its trip based on its distance and time from the crossing. Guess what this crossing is at your halfway point? That's going to be your vertex, but what's also neat about your vertex, because this is our time. Time is representing our x, and then y is representing our distance. So if we're talking about where we're halfway point at this one spot, that's my vertex at 0, 0. Because it's when I'm there and it's halfway through. Okay? So then to figure out everything else, we're going to consider the time before you arrive at a destination to be negative. So if I'm at -1, how far am I going to be away from this crossing? Well, I'm traveling at 50 miles per hour, so if this is 1 hour back, then I'm guessing I'm going to be 50 miles up, and I'm going to go by a scale of 50 here. So -1, 50. If I'm 2 hours before I leave, guess what? I'm going to be at 100. If I'm 3 hours before I leave, I'm going to be up here at 150. So I'm going to be 150 miles away. So that's before I leave, or before I get to that halfway point. Now I'm at the halfway point. So what's my distance going to be from the time I cross it? Well, now I'm talking about positive values here. So we're going to have +1, and I'm going to be 50 miles away from it. At 2, I'm going to be 100 miles away from it, and then at 3, I'm going to be 150 miles away from it. I guess that point's a little off, but you get the gist. Absolute value function, this models it. The only thing, you don't have to write it, but you could write it. The equation that this is representing, its distance equals the absolute value of our x, which is time. So distance equals absolute value of t, which you had from your notes. Make sure if you have questions, bring it in tomorrow, we'll talk about it. I'll also go through how to graph it with your graphing calculator in case you can't find the absolute value feature. Have a nice night. We'll see you tomorrow.